I want this to be a technical engineering presentation.
Don't worry, you know about it. Well, hey guys, I met Tarek yesterday on our previous meetup that we had. I was giving a talk with the Blackboard. I don't have a Blackboard now, so we're gonna have to just imagine certain concepts. I am developer of Haskoin. Haskoin is a Bitcoin implementation of the Haskell implementation of the Bitcoin protocol. We wrote the whole Bitcoin protocol, we reimagined a lot of things in the Bitcoin protocol on the Haskell programming language. And you'd say, well, yeah, like every other implementation, every other language that's out there, dull and boring. Not quite. When I started programming a few years ago, 8 years ago, my first language that I was using was Perl. Perl was a very expressive language, a very funky language, quite crazy syntax, not like anything else, and it was very fun to write in Perl. Perl is a fun language because it lets you express very complex ideas in very little code, and the code usually works fine, and it allows you to. It has all this incredible amount of libraries that are very documented, and I had a lot of fun. But suddenly, I came to a point where Perl was a language that was limited. I couldn't do certain things with it. It was bad for asynchronous applications. It was bad for certain things. So in my journey through programming, I had to leave Perl behind at some point to be able to build more complex applications. At that point, I arrived and I went back to the marketplace looking for programming languages, again, to see which programming language I could use that could manage to do more things. At the point I was already familiar a bit with JavaScript. It was a language that had certain cool features, but it was quite difficult to get it right. There was many errors that you could do in JavaScript that would only show up when your application was running in front of the client, usually in the middle of a presentation. That's when the first version of the application would crash, because the client or the person that was using it would do something that we never used when we were developing, and the application would go to hell. And that was pretty bad. So we had to really test the application very thoroughly, and that became quite annoying, because it was a lot of boilerplate, a lot of tests that were just testing for things that were done that the programming language would have taken care of itself. Like, is this an integer? Is this actually a string? Is this an object? Is this what I am expecting it to be? And many programmers of dynamic languages tend to say, but type errors are the least of your problem. They are the last thing that will happen to your program is a type error. Well, that's wrong. My experience programming, type errors was what I made the most. So maybe that's because I am the kind of programmer that makes type errors, but I got annoyed by the lack of a type system in my programming language. So then, back again into the marketplace, looking for a new programming language to code again. So then in the marketplace, I met my friend. I was working already with my friend, Philippe Labrade. We worked at JP Morgan in Switzerland, very boring organization, but we were given a particular place, a particular work group, where we were kind of left alone to do what we were good at, programming applications. So my good friend Philippe studied with Professor Martin Odersky in the University of Lausanne in EPFL. And he came to me and he said, you know what functional programming is? And I said, well, like every program, like, programming with functions, duh. And he says, no. It's not programming with functions. It's a different thing. It's that the functions are an actual thing that you can transfer around the program and you can give to other functions and you can just compose them together and do great things. Like, yo, this is kind of crazy. Can you just explain this to me a bit deeper? So I just read a book by Odersky. I don't have time to explain this. Of course, I got the book by Odersky and I was reading the book and I got really hooked into the paradigm. I said, why is it that not everybody is coding in this way? Because this seems to be the right way to program. It seems to be the right way that leads to us not making all the mistakes that we all make all the time while coding. Surprisingly enough, when I mentioned this idea of functional programming to people, they would look at me and say, you're such an academic, you're stuck up. And I say, no, I'm a high school dropout. Come on, I just learned about functional programming by a friend working at the company doing web applications. I'm not an academic. I don't see functional programming from the eyes of a person that has a formation in math or computer science. I just see it from the eyes of practical programmers who have been programming for many years and have been having these kinds of problems with our applications that I write. So I learned Scala. I programmed a little bit in Scala. I used it a lot, but something annoyed me about it. There was there was this massive JVM pile of middleware between me and the operating system that was really annoying me at some point. I was saying, why do I have to just set up all these things at this level? And it seems that the language was designed with a lot of trade-offs to be able to map into the JVM, to be able to map the functional programming paradigm into the paradigm that ran on the Java virtual machine. So I decided, let's go back into shopping. And also, the book sometimes mentions things that annoyed me. So the book says, oh, look at this example program that I'm going to show you in Scala. Look at how cool it is. It's called a monad. And I'm like, what the hell is that? And then, well, I couldn't understand what it was, and it was annoying me because there was a concept in the programming language that I was choosing to use that I could not understand the thing. So I said, what's a monad? And I stumbled upon Haskell. So I thought that Haskell is the language where all these cool things come from, it seems, or the latest generation of cool things in functional programming come from. So I decided, well, let's delve into it, let's learn it. It took me a year to understand what a monad was, and at the end it was such a simple concept. And so I took Philippe and we started working on this implementation of Bitcoin in Haskell because we understood it to be the most secure way to program. And I'm going to try to explain without the whiteboard why it is the most secure way to program. First of all, who of the people in this room have not programmed in any language at all? Okay, that's good. Who in this room has programmed JavaScript? Okay, well, good. Who in this room has coded C++? Oh, poor guys. Okay. So what happens with, for example, a program in a lower level, high level language that rests in the lower level of the abstraction scale, like C or C++? Have you tried to manage memory yourself and got memory leaks in your C++ applications? Have any of you got a memory leak? No? Really? Okay. The other ones that say they program in C, they don't. A memory leak occurs when you, for example, have to allocate memory. You have to ask the operating system, hey, give me this chunk of memory so I can work on it. And then the operating system will have to tell you how many bytes you want. How awkward is that? So you have to tell it, oh, I want this amount of bytes, and if you don't know how many bytes you want, but you know more or less how many things you want to store in this thing, you just tell it, okay, well, give me the size that thing occupies on memory in my machine multiplied by a byte, and then you get the amount of bytes, and then you use that. But there's nothing preventing you from trying to store more data or put more data into this allocation that you just made out of the computer memory. But what's more creepier is that the program will not crash if you try to put stuff beyond the end of your data structure. So if you want to program a very secure application using a language that allows this kind of freedom to you, you will end up writing something messy at some point, because the language will not complain until it's very late. And well, who is familiar with the Heartbleed vulnerability in OpenSSL this year? Everyone is familiar with that. What happened in this one? It's the same thing. You are trying to access a position in memory that you have not mapped into that particular variable. Why? Because the language does not offer any features to prevent you from doing that. Because you are coding at the lowest level. And the people that like this programming language will tell you, well, you get power, you get performance. And I say, yeah, it's great that you get performance, but in an application of like OpenSSL, performance is useless if your application is going to give all your secrets to whoever connects from the internet to your software, and the security of all your computer, your systems is going to be compromised. So then you have to kind of step back and say, okay, maybe in this case, performance is not as important. Maybe in this case, something else is important. Maybe you're developing a game, well, performance will be more important than anything else, and you will have to make the trade-offs, and it doesn't happen, it doesn't matter if it crashes once in a while, as long as your people get a good frame rate. But in applications such as Bitcoin, for example, which is crucial, which is so important that everything works perfect, that security is nailed correctly, using languages like C++, it's an invitation to a hack eventually. The Bitcoin code, fortunately, have not been exposed to many vulnerabilities that have made it that have been very bad, that have caused people to lose money. But the reason this hasn't happened is because the developers behind Bitcoin are very competent, extremely competent. They are so competent that they see these things when they happen, but you are relying on the human being competent in a massive piece of software with a massive amount of code that is written in a style that makes it very hard to audit. I myself was reading the Bitcoin code a couple of times, getting some snips, bits and pieces to put in Haskell, and I found bugs. And I'm like, oh, look, this bug with the time, with the clock, and I said, no, there are more. Don't worry, there are even bugs in the consensus protocol. I'm aware of a few of them now that I've read that part of the code. So it becomes imperative to just move away from this this style of programming. And why? What does Haskell bring to the table that C++ or JavaScript or Python doesn't give you? What is it? What is that you really get from it? Well, you get type safety. Type safety is something that people are not unfamiliar with these days. Languages like C++ have type safety. You can tell it, this function only can take this type of data. You can tell languages like Java what type your data comes, the data that they accept. Usually they have very rudimentary type systems that are quite constraining, especially in Java. It's very verbose. You have to, whenever you write a variable, let's say you're going to create a list of integers, you have to say, imagine it's a list of integer numbers, and in this list of integer numbers you're going to declare it with something that is actually a literal. You are going to provide the numbers themselves in the code. Well, you still have to tell it, look, I'm going to give you a list of integers and equal, and then you give it the list of integers. When the programming language are perfectly well known that this list of integers was such. That's what Scala gives you, and the type system in Haskell, which is a Hindley-Milner type system, gives you. It's called type inference. It's where the type system does not get in the way, does not disallow you from finishing your work. You're busy, you want to get your code written, and you want to get it fast. And you don't want to be dealing with a type system. That's why people use Ruby, that's why people use Python, that's why people use programming languages that are dynamic. But the thing is that there are programming languages like Scala, like Haskell, that have type systems that you don't have to deal with them at all times. You can just leave the program, the language, the compiler to figure out the types of the things you have put into your application, and it will detect type errors even if you haven't provided type information. So that's pretty good. But what else? What else do I get from Haskell that's so cool, that I like so much, and that compelled me to write Haskoin? Well, you get something that is called context, monadic input-output. And this is a concept that's very alien. But who in this room knows what monadic input-output is? 3 people. 4? 3? 4. Well, 4 people. But to the rest of the people in this room, this concept may seem a little strange. When you read a book of Haskell, or you read an article on the internet about monads, and they tell you about how monads work, you are not going to understand anything. I didn't understand anything for a year. I read many articles until the concept clicked. Because what happened is that the articles were trying to do the thing the other way around. They were trying to say, this is the math, and this is how it maps into the monad. And for someone who knows category theory, that must be great. I never knew category theory, and I still don't know it. But I know for a fact that monads are a useful concept, and that they are understandable by a regular human being. You don't need to have a PhD in maths and computer science to understand what a monad is. So why does it help you? Why is it so cool? Well, imagine you have a computation. Okay? Your computation is, let's say, an addition. An addition is a very simple computation. You give it 2 numbers, you obtain a third number, which is the addition, the sum of these 2 numbers. This computation doesn't require any context. It's a contextless computation. Whenever you give it the 2 numbers, you obtain the same 2 numbers. The computation itself does not write to log files, does not print to screen, does not send data to the network, and definitely does not launch nuclear missiles. This computation is completely self-contained. So if you have a computation that's self-contained like that just it doesn't affect anything else, this computation is what we in the Haskell world call a pure computation. And a pure computation is something that you can run many times over, and you can run in parallel, and you can run in a different processor or different computer, and you only care about the inputs and the outputs. In fact of the matter is that you can just compute the computation for the same set of values once, and then remember the result and just give the result back whenever someone else asks for that data, like a sort of caching. We call it memoization. So these pure computations are things that are cool because you can run them in another processor. You can parallelize them very easily in your computer. It just requires that your computer, your programming language knows which functions are pure and which are not. But if you're using C, if you're using JavaScript, if you're using any other language, you won't know this. Your language doesn't have the capability of understanding whether the function that it is being called is a pure function or not, because the language is not like that. You need a language like Haskell to be able to do that, because the Haskell language by default has functions that are pure. So when you declare a function with certain parameters and you declare computation that happens within this function, the language by default doesn't give this function any context and doesn't allow this function to access anything outside of its inputs and return anything outside of its outputs. It's a very powerful concept. But then you tell me, and how the hell am I going to write a software application in that way? How am I going to do a real life program if I cannot just cause the program to launch messages into the network or to print output to screen or whatever? How am I going to do in this case? Well, that's where the concept of a monad comes in. That's where monadic input output is. And this very interesting mathematical concept allows you to tag a function with a context, allows you to say this function, this computation has a context, has a determined context, and you can be very, very specific about the context you give your computation. And if you're very specific about this context, that computation will only have access to what you have given it in context and not to anything else in your system. Say your application can know, your function here is a function for retrieving data from a database. And you have a generic database context that allows you to access the database. But this application, if you give it this particular context, it will not be able to go into the network and fetch data from the network cable. It will not be able to go into a random file in the disk and access data from that random file in the disk. It can only access that database, what that database context allows. And it could be a read-only database context that allows only to read the database, and that particular function is tagged that way, you know for a fact it will not be able to do anything else. And your compiler also knows that. And then your compiler can perform optimizations on your application, can perform decisions on your application that it could not perform if it was a compiler of any other language, because it does have more information about what the program actually needs to work. This monadic input-output and this context can be extended to the point where you get a part of the application that can perform absolutely everything. And usually the application enters through a function that's called main that is running on the input-output context and can do anything. That's the entry point of your application. And from that point, you kind of organize all the input-output of your application. That guy there, the main function of your application, becomes a sort of a broker of data. It just tells, open these files, set up this context, connect to this particular database, set up these network connections here, and set up this listener here to listen for these network connections. And then these listeners, these parts of your application will start to call pure functions. And from then on, once you call a pure function, anything that pure function calls is self-contained and it's transparent, it's referentially transparent, and you can run it on any CPU, and you can unit test perfectly. And this is the holy grail of programming today, because you are programming now machines that have multiple processors, that you want to use them, and you are programming applications that are asynchronous, that depend on multiple communications at the same time on the network, and you don't want to have global variables that the application is reading from without you knowing that this has actually happened, and you get this information from the context of the application, and then the compiler can perform correctness checks on the application and can figure out whether these contexts are compatible to one another, or whether you can do or not do certain operations. There are contexts as well that are more dangerous for when you want more control, but you can constrain this control. So Haskell and functional programming in these languages are about constraining side effects and controlling the side effects of your application to a point where you really, really know what it is doing, and you can write applications and software and programs that you can think of. Another benefit of this scheme is that you don't have these mutable data structures at all. You cannot change the value of a variable. How is that? Then you're going to ask me, how the hell do I do a loop? How the hell do I go around, like from I to the length of list, from 0 to the length of list? That's an error, by the way. From 0 to the length of list minus 1, right? Yeah, that's better. then you have to iterate. How many times have you seen that error in real life? How many times have you addressed a list element that didn't exist, knowing in advance the length of the list? How many times have you used less or equal than the size of the list instead of less than the size of the list? Every programmer has made that mistake. Everyone in this room at some point of their lives, and many of you will be ashamed to admit that you are still doing it now, and you probably did it yesterday if you actually programmed. So this is what a language or a program written in Haskell can do for you. This is what this kind of languages can do for you. So sorry for Haskell being this academic thing that was kind of hidden behind in academia by very introverted people that don't speak to anyone outside of their campus, because they have actually created a very good idea and we need to yank it from their hands and use it in the real world. And this is what I am doing with Haskoin. With Haskoin we have created the cryptographic code for Haskell, the cryptographic code that does the critical parts of transaction signing, the critical parts of the Bitcoin protocol, the Bitcoin transaction specifically, Bitcoin wallet handling, are being done in this very, very constrained and very secure context. We have even implemented deterministic signatures, so to avoid the signature part of an application, the signature of to require outside context with random data that can go wrong. And we have converted all the transaction signature or transaction verification into a self-contained process that is very easy to unit test. We have massive amounts of unit tests that we have been managed to make with this. The refactoring of this application is extremely easy because every function that requires, every function will receive all that it requires to work with as an argument, and it will return anything. It will return its return as its output, and it will not have access to anything else. So you don't have to test whether this object changes this other thing. Back to iterations and how do you deal with iterations if you don't have mutable data structure or mutable data of any sort. Well, you use recursion. You're going to tell me, what the hell, recursion? Who codes in that style today? Well, nobody, not even us, we code doing recursion. We in Haskell have abstractions for recursion. We have maps, we have these first-class functions that allow us to do this. You have a list of things, of values, and say, I have a list of transactions, or a list of keys, and I want to have a list of transaction outputs. And I want to get those transaction outputs signed by these keys. Well, I just map the transaction outputs through the list with a function that acts upon each transaction output and iterates over the elements of the list, not doing an iteration, but through a map, through a functional programming construct that allows you to easily do this. And the power of this as well is that as you can pass functions to other functions, you can construct these higher level functions that do abstract things in your application and save you a lot of work. So a function language like Haskell is an extremely powerful tool that allowed us to write a full Bitcoin wallet implementation in a short amount of code. You can check out GitHub and you can see your code. It's public domain. It's not even licensed or anything. It's licensed with the unlicensed because my colleague didn't want me to license it and to do what the fuck you want to public license because it was too bad worded. But that's the idea, the philosophy of it. We want the Bitcoin network to become a more secure network, and we want to build this, and we want to turn it into a full node, and we are working with Bitcoin developers to improve the consensus rules on the Bitcoin network so that we can have alternative consensus implementations, because I think that will be essential for the evolution of the network and for the security that Bitcoin deserves. And check our GitHub, it's called Haskoin. If you're not a Haskell developer, don't you despair. You can also use our application. Haskoin has a daemon called Haskoin Wallet that exposes the wallet features of Haskoin in a very easy to use JSON RPC API. So you get a JSON RPC API, REST API that is more powerful than what you get with Bitcoin D, with multi-signature hierarchical deterministic accounts, multiple accounts. You can do your own key derivations. You can do it. You can do your wallet any way you want. You have loggable database backends, and you can do this without knowing Haskell. You can install it in your system. You can use it as a backend for your Bitcoin application, and it works perfectly well. I am also an employee at Coinify. I am in charge of securing different transactions at Coinify, by the way. Working for Don, who has been here presenting before, and they are using Haskoin as well for securing the most critical part of transaction signing. When most of the applications.
Whoa! Tom's using Haskell.
He's using Haskoin.
So what did they do with Haskell?
Oh, we're doing it. We're doing the security part of the application, the actual signing of the transactions are being done on a separate server. Well, we have separated the signature of the application, so we put it in a separate server, and the Ruby application communicates with this outside server that works as sort of a signing oracle and signs the transactions. And the code for this signer was done in 70 lines. 70 lines.
What were you guys using before Haskell? Was it like you just started with it?
We didn't have anything. We were signing on the same server that had the web server, and I said, no, let's just change this, let's move this around. And he, well, Don was saying to me, we have to change this. How can we, do you have any suggestions? I said, yes. 2 hours later, I had a Haskell code to do the signing part in a separate machine. That's how flexible and that's how easy to use it is for a Haskell developer, but for a non-Haskell developer, you have access to an entire web. And you can check it out, it's very well documented. You will find documentation both for the Haskell parts of the code and for the API, so you can just install it on your server and use it. Currently, we don't have a full node yet. We are working on that. We will have a script interpreter to interpret different scripts as they come in. And we have to work more with the consensus rules because we know for a fact we have to be bug by bug compatible with the consensus protocol, but what we want at this point and what we advocate and what I said in the mailing list a couple of days ago, we want Bitcoin consensus rules to change, to have the bugs fixed so that it can be properly documented both in paper and then transliterated into another programming language in a safe way. So thank you very much for having listened to this presentation. Any questions? Yes, go ahead.
What's a good starting book for functional programming?
A good starting book. I just loved the Learning of Haskell for Great Good by Pierre. But if you're not into reading so much because your eyes strain, you can just go into Coursera and look at the wonderful course by Professor Martin Odersky, Functional Programming Principles in Scala. Scala is a very good functional programming language as well. It has some interesting concepts like actors, and it's compatible with the regular function programming style, so that you won't be so you won't hit the paradigm. You will have time to transition.
Yeah, I would second Learning of Haskell. That's like one of the best learned programming books I've ever actually read. Yeah. Besides being about Haskell, it's really good.
And even if you don't program in Haskell, read the book so that you know how miserable you are when you program in another language.
What was the title of it?
Learning a Haskell for Great Good. It's actually available for free online. You just can read it on the web page. There's Real World Haskell, also available free online. I think all Haskellers want to have the information out there, so they publish their books for free. Yeah?
Sort of a two-part question. So, taking, say, a private key material, and I want to create a digital signature from that private key. I think what you're saying, and correct me if I'm wrong, is that you can create a function that guarantees that when you put in the private key material, you get an output, and there's no way that it could possibly be leaked in that process. There's no code that could have executed that could leak it.
Actually, yes, that's pretty much it. That's the guarantee. Provided that the compiler is secure, provided the machine you're running the program is secure, provided that the machine that you're running the program in is not running on the same processor co-opted or co-used by another machine that's dangerous and that's hacking you, but that's yet another story. The program itself is guaranteed correct. Now, what happens in the backend in your machine, that can change. You can have a sniffer looking at your memory contents, or you can have something happening there that could hack it. So it's not like you're going to run a secure program in a non-secure computer and you're going to run it. You still need to practice computer security. This is not a silver bullet, but at least we can guarantee a lot better security at the software level, at the code level. So that's what we want.
And then the second part is the context that you said when you're executing that function. There's a context in which you're able to execute that function.
Yes.
So what kind of context would you put on that, say, private key material as an input? Like what abilities do you have?
Well, we have actually two versions of the signing function. I'm going to get technical here. We have a contextful signing function because, let me just explain a little bit about the elliptic curve signature. Don't worry, don't get scared. I'm not going to explain how the whole elliptic curve signature works. I'm just going to explain what it needs to be able to sign a transaction. When you want to sign a Bitcoin transaction or any elliptic curve transaction, the elliptic curve signature protocol or standard states that you need 3 pieces of information. You need whatever you're going to sign, you need the private key you're going to sign it with, and you need a random value, k. So that random value needs to come from a source of good randomness. You remember, is anyone familiar with the Android bug last year? Yeah, you are? Good, because that was my 15 minutes of fame. I discovered that bug. So, yeah. The signing function, that prompted Peter Weir to work on I'm not a cryptographer, but I happen to know a little bit about it at this point because of my work with Bitcoin. The scheme requires you to have a random number that comes from a true random source. If you ever reuse the same random number to sign 2 different messages, you will end up revealing the private key. There is a very easy to follow arithmetic computation that runs in polynomial time that will give you the private key. So it's very easy. So you don't want to do that. You want another scheme. You rather, if you need the signing function that needs context, that needs the monadic context to obtain randomness from, because every time you sign even the same message, you will get a different signature because there is a factor that comes that's random. Okay, that's why the function needs to run inside this context because it's not deterministic to its inputs. The source of randomness comes from your operating system, and your operating system can be anything from a proper Linux machine with a proper random number generator that's considered generally secure with sufficient sources of entropy, or it can be something like an Android phone that has a bug on the random number generator sources and that will not give you enough entropy and that will make it very likely by the birthday paradox to eventually have your private key leaked if you sign too many transactions, or basically if you spend too many times money from the same address. And as you know, the Android wallet does that. It reuses the address every time. It doesn't generate a new address for every receiving payment. So it actually encourages you to spend a lot of Bitcoins from the same actual account. So it will probably lead to that. Now it's fixed because Andreas Schildbach actually plugged to another source of randomness once I discovered his bug and it was all fixed. But yeah, these kind of things happen. So we have another function that uses Peter Weir's scheme called deterministic signatures. And we only obtain the information that is needed to sign the transaction from the transaction and the private key itself using a hashing function. So now the function becomes deterministic, which makes it very easy to unit test because the signatures are always the same coming out of it. And you don't need a random number generator in your signer. So at this point, you can start using, for example, this scheme in a hardware device where finding a proper source of randomness is difficult. So you can create embedded devices or even microchips that can sign different transactions from an NFC card or something, and you don't need to have a source of randomness in that device. And sources of entropy in devices like that are very hard to come by. Usually your computer has enough sources of randomness because it has a lot of sensors inside the computer. And these sensors can be, the information, random noise from these sensors can be obtained, can be gathered, and can be used to generate entropy. And we have then 2 signing functions. So we have the contextual and the non-contextual. The non-contextual doesn't really need anything from its input. It just needs the private key and the transaction, and then it signs the transaction and gives you a deterministic output. You also wanted to ask me?
Yeah, I just had a quick question of the need for this in the cryptocurrency community, considering the fact that 90 out of 100 or 9 out of 10 cryptocurrency projects are written in C++. We must have the most brilliant programmers in the world, or the most arrogant programmers in the world. I'm not quite sure. I don't see the need for it. But really bless you.
Yeah. Honestly, what I think it happens is that people are not familiar with this scheme, with the way it's programming that Haskell proposes. Since people are not familiar with it, then they are content to use whatever tools they have at their disposal. They are well documented and all. But what I try to bring here, what I want to you get from this is get the familiarity with this, so that you understand that there is another way of doing things, and that it's more secure, and that it is more correct. And a Haskell application is a compiled program. It runs on machine directly. It does not require VM. It does not run slowly. So you will get performance, the same performance that you would get for a similar Java application, but which is already Java from today, not Java from 2000. Just to clarify. And yeah, it's performant. It works fine. So use it.
One comment that I would make to your statement is that absence of faults in the system doesn't equal absence of, or evidence of absence.
Exactly, yeah.
Oh, I
Yeah.
agree completely, 100%. It's just, I get so frustrated when I see every goddamn new
Something
project
else.
out there still using C++
Yeah.
and copying the make files from.
At least they're copying them and not writing their own. Something else, the code that, the pure code that deals with certain things, and we have tried to make most of the code pure, in Haskell can be automatically converted via software conversion into entries for Isabel or Cog. These are proof engines. So if you have an intern or a mathematics student with a lot of free time and it has a very high level of Asperger, then you can give it this code and they will mathematically prove it for us, which will be great. We will have a mathematically proven implementation of Bitcoin, which would be great for security. Yes?
Did you consider using crypto?
Crypto?
Crypto? Haskell DSL, crypto protocol.
Oh, no, I haven't seen that. Actually, I wasn't familiar with it. Oh, good, thank you.
Have you tried compiling to HAL-VM so you could actually run directly in the hardware?
No, I haven't done that. I have just done plain Haskell. We focused on the code. I didn't know these things. I'm a new Haskell programmer. I've been programming Haskell for 2 years. But definitely worth taking a look. Yes?
Did you try to parallelize your code?
Not yet, because whenever we have parallelized it, we have actually obtained less performance because there is some overhead that the parallelization generates, and the code is very fast already and does things that are quite trivial. But yeah, parallelization will occur. It's occurring now, but at the level of the high-level part of the code, the one that gets, for example, messages from the network. It spawns new threads, but you cannot spawn many threads. But if you spawn too many threads, the overhead of spawning threads will kill the benefit from the parallelism. And computers are very powerful today. They run at 2,000 gigahertz, so a few elliptic curve signatures get done very quickly. For downloading the blockchain, once we get the full node, we will definitely parallelize the application. There are schemes for parallelization for Haskell programs. Some of them work at the IO level, so at the monadic every context level. But some of them also can be used at the pure code level. So you can give it hints so that the compiler knows that it should parallelize that application. But it by default won't parallelize it, because even when it can, the overhead can be too high. It doesn't know what the runtime of that function is going to be. I would guess that in the future, Haskell compilers can be imbued with the ability to analyze performance or profile a program in real time and parallelize accordingly. That would be actually great. But the compiler has the information to do it. But it's just that it's a titanic work for compiler writers to do this kind of work properly. So,
I gotta call the last question because we gotta wrap up soon.
okay.
So, anybody got a last really hot, awesome question?
The last question, make it good, make it count.
Matt.
Matt, great.
No, so I did have a few questions, but I'll put it short and I'll put it down to one.
Don't worry, we have stuff later.
You focused a lot on how to make the software correct in the traditional sense of software engineering, where you don't have memory leaks, you don't have threading bugs, whatever. But you didn't focus nearly as much, right? There's over however many years of software engineering, we face these, and we've kind of as a global software engineering community really trying to address these bugs in a number of different ways. But you didn't focus kind of at all on the new bugs that these consensus systems have generated. And you mentioned briefly, right, you have to be bug for bug compatible with Bitcoin's consensus for a full node, but even as an SPV node, you have to be bug for bug compatible with a lot of parts of Bitcoin.
Yeah.
So you didn't really address, I don't know, if you guys, what your approach to that?
We have been looking at the code in Bitcoin. Most of the code we based on to write Haskoin comes from Bitcoin J. Bitcoin J is certainly not bug for bug compatible with Bitcoin D, or at least it's a different implementation. It takes a different approach. So there certainly are things that will not be bug for bug compatible. The problem with bug for bug compatibility is that the bugs we know, we have made them compatible. But the bugs we don't know are the problem. So how can we be compatible with bugs we don't know? The thing is that we can't.
Well, I would suggest you guys have an approach to that, right? Because there are approaches to this, and there's like there's some formal verification work where you can prove, like compile out the LLVM on both sides and prove equivalence.
Yeah, but that is not going to work on this Haskell program. That you cannot do between a Haskell and a C++ program.
No, actually you can compile to
Yeah, but it's not gonna be the same, the binary code is gonna be different. The way a Haskell program works is different.
That's the point, though. You can take a function. I mean, you create essentially a function in C++, or especially the script execution, where it's programming style has syntax, etc.
That's something to consider.
And then you can compare that. I mean, like to the point where a script execution is pretty functional already. It doesn't really have any side effects.
Yeah. Actually, we've seen that you guys have cleaned that up very well in the last few years. I like the work you have done there. It has made it very easier, much easier to read for us and to work with. But the problem is that these bugs need to be documented. And when I say documented, it's English. Before we can really make, we need to make Bitcoin protocol specification into paper, into English, even with the bugs. If possible, not with the bugs, after we fix the bugs. And then we just make it into a specification.
I'm concerned about like that's playing more, right? You're never gonna fix everything. You're never gonna understand everything.
Well, but you can the stuff that has not that is known so far. That's a lot. There's a lot of stuff already known. This stuff can be put into a BIP, can be submitted for a hard fork, and we can just schedule hard forks every 3 to 5 years to fix bugs. Or if there's an emergency ones, well, we can do that more often. I don't know. We must get a system done to get rid of these bugs. Many people say are cowboys. Say, oh, but if this bug we don't know any way to exploit it, then we don't care. But the thing is that even if there's no currently known way to exploit the bug, there will be a very smart 16-year-old kid with a lot of Asperger that we will find out. I just have a little bit of
Nice. Thank you, Jean-Pierre.